Okay, looks like we are live. Where is Zoom? There we go. Okay, so welcome everybody to the Quantum Matter Seminar. And today it's my pleasure to introduce Alfredo Levy-Yeyati from the Autonomous University of Madrid. And with that, please, Alfredo, please begin your talk.
Thank you. Thank you very much, Phil. Thank you, Adrian, for the invitation to give this seminar. So I would like to tell you about work that we have done on Andreev states in hybrid nanowires. This is work that we do at the Autonomous University of Madrid, and is in collaboration with many experimental groups, with some experimental groups, in particular, the Quantronic group in Saclay. I'm going to give more details later. And this activity is associated with this European project NQC on Andreev qubits, which I'm going to tell you more later. So let me start in order to give you an idea about the type of states we are interested here. Because Andreev states are there's a very general concept. Any, say, spatial modulation of the gap of the order parameter in a superconductor may lead to some bound state. And for instance, one can think of Shiva states when we have a magnetic impurity in a superconductor, or we may think of surface Andreev states when we have a D wave or ITC superconductor at the surface. We can have bound states, which are also an example of Andreev states. Even at an interface between a Dirac-like metal like graphene with superconductor, we may have interface bound states, which are also Andreev bound states. And for it, example also, Majorana, the so much searched and elusive Majorana bound states are a kind of Andreev states which appear in a topological superconductor at the edges of a topological superconductor. But the type of states we are interested in this work are the Andreev states which are associated with the Josephson effect. And this is an idea which is already can be traced back to Kulik in the 70s, that we can understand the Josephson effect as mediated by multiple Andreev reflections. For instance, in an SNS junction, we may have an electron in the normal region, which is reflected as a whole. The Cooper pair is transferred to the right lead, and then the whole is reflected back as an electron, and Cooper pair is injected. We may calculate, we can evaluate what is the condition for the Andreev bound state by calculating the phase that is accumulated in such a process. Delta here is superconducting phase difference, and these are the momenta for the electrons on the holes. And this is a transcendental equation which is imposes the quantization condition. And if we solve such a transcendental equation, what we obtain is a set of discrete states which are dependent on this phase difference. So these are current carrying states. So these are the states which carry the supercurrent in such a function. So this gives a modern picture of the Josephson effect in any type of weak link, not only these ones, but many others. No? So in particular, for instance, one can solve these equations for the case of a short contact, a single channel short contact, where you have some barrier in the middle with some transparency. And well, you can solve Bogoliubov-Jenets equations for coupling these two regions. And what you get in this limit, lengths much smaller than superconducting coherent lengths, is a dispersion relation given by this expression here, where delta is the gap, the square root of 1 minus tau, the transmission, sine square of delta half. And this gives, well, there are positive energy and negative energy states. I'll only plot here the positive energy state, which would have, for a given transmission, not perfect transmission, would have a dispersion like this one. And if we derive the energy of the state with respect to the phase, we can get the supercurrent at 0 temperature, let's say. And in this short junction, this is the whole supercurrent through the junction, and this was worked out already in the early 90s. No, the connection between the Andreev bound states and the supercurrent in a weak link. However, it was not until rather recently that direct evidence of the states was obtained in experiments. So we always have like indirect evidence like supercurrent, noise, and all this type of information. And what these recent experiments using circuit-QED techniques, I'm going to explain a bit, are giving direct access to these states. And these are particular results from the group of Saclay, where what they do is to take a particular realization of a short junction, which is an atomic contact of aluminum using mechanically controllable rejection techniques. This is placed in a loop, and the loop is coupled to a microwave resonator. The phase across the junction can be controlled by the flux through the loop. And by shining microwaves, one can get a spectroscopic signal of the excitation of the state. So the frequency that one measures for this one channel contact is twice the energy of the state. And one can perfectly fit the experiment with a single parameter here, which is the transmission of the channel. So, and not only this is direct evidence on the Andreev bound state, but also what you can do with the circuit-QED technique is to do time resolve experiments, and in particular to probe these Rabi oscillations when you excite this transition and you see the evolution after this excitation. You can see the Rabi oscillations, which demonstrate the possibility of quantum manipulation of these states, or coherent manipulation of the state. And this shows that these states can be useful for quantum information or for producing a qubit. And in particular, well, the idea of the Andreev level qubit is a rather old idea, more than 20 years was in the literature. The idea is that one can store the information on these states. This is like a two-level system. It's a kind of superconducting flux qubit, but instead of what happens in conventional qubits, this is based on a single quasi-particle excitation instead of the collective excitations that one has in a conventional superconducting qubit. And it's the idea that we try to explore in this European project NQC, because there is a promise that by playing with these excitations, one can get improvement with respect to conventional qubits, in the sense that one can get more dense, or the distance between qubits can be reduced, and the density of qubits can be increased. Okay, but I'm not going to talk much about this. But let me say that what is changing a lot our view and understanding of this type of Andreev states are these developments, also experimental developments on semiconducting nanowires. Semiconducting nanowires that can be produced in high quality, especially, for instance, a group of Copenhagen by Peter Kostrup and Jesper Nagar, which they produce this type of nanotubes, which are indium arsenide semiconducting nanowires, which are fabricated with high degree of perfection, reaching almost the ballistic limit, with an epitaxial aluminum layer, which induces a hard gap. And these nanowires, the combined superconducting cover and the nanowires have all the ingredients which are needed to produce Majoranas in the end. But we can use them. In the experiment from Saclay, for instance, they use these nanowires to fabricate a junction like this one, in which one when we can remove the aluminum cover in some junction in the middle, some region in the middle with a length which is controlled, and produce a Josephson junction like this. So one can have many questions about the Andreev states in such a system. For instance, one can ask what is the effect of a final length in the spectrum, the Andreev spectrum? What is the effect of spin orbit? Of course, because these semiconducting nanowires have a strong Rashba spin orbit. And eventually, what is the effect of electron-electron interactions also may play a role in these devices. So I'll try to give you first the theoretical understanding of all these effects in such junctions, and then the comparison with the experiment from the Saclay people. And well, let me also show this slide, because this has some historical interest, because this was the first data we received from the Saclay people in 2018, which looked like hopeless, trying to understand the spectrum of this nanowires, function of gate and function of flux. But at the end of the talk, you may try to see how much out of this rich structure we have understood. And let me start by discussing the effect of the length, but this is something which was known since the 90s. So if there is in particular a very simple and elegant model from Bagwell, which he considered a channel, single channel, where there is some scatter in the middle. And for this situation, he calculates this transcendental equation, which depends on the transmission, the phase, and the position of the scatterer in the middle. And this parameter lambda is the ratio between the length and the coherent length. And as you increase this parameter lambda, what you see in the spectrum, Andreev spectrum, is that one gets more and more states inside the gap. Essentially, this parameter lambda tells us how many Andreev states there are in the gap. And the states, as we increase the length, look very much like the bands in a one-dimensional solid. We open gaps at the crossings between the ballistic states. The dashed lines could correspond to the case of perfect transmission, and when you put transmissions more than one, you open gaps there between the states. So this is the effect of length. Now, what's the effect of the spin orbit is the other question. And suppose now for having the effect of spin orbit, we have to consider, let's say, a two-dimensional model for the wire in which there is some confinement in the y direction, let's say, and we have a Rashba term associated with an electric field, let's say, perpendicular to the plane. So in principle, the confinement gives rise to subbands, and the spin orbit associated with the longitudinal movement gives rise to splitting of these levels, splitting of these subbands. And then associated with the transverse momentum, we have another term which couples to the spin in the x direction. And these couple different subbands with different spins. Eventually, leading to these anti-crossings there. So that if we place the chemical potential somewhere in the middle of these subbands here, one would get states with different spin and different velocities, Fermi velocities, and this would be the effect of the spin orbit in such a nanowire. But let me stress that in principle, spin is no longer well defined because we have a spin orbit. There appears a spin texture in the y direction. However, if we still have inversion symmetry in the wire, there is another conserved quantity, which is we can define pseudo spin, which is the product of the subband and the spin degree of freedom. And now, if we go to the superconducting case, we take such a wire in the ballistic case, let's say, and we impose the Andreev reflection at the edges of this channel. And well, if it's ballistic, what we get is a set of Andreev states which are now split because the lambda parameter is different for the different Fermi velocities, because the Fermi velocity determines the coherent length. And for the slow mode, we have a smaller coherent length, and then the length, effective length, is longer for the slow mode, and this gives rise to less dispersive Andreev state, whereas for the faster mode we have another more dispersive state. So this you see already for finite phase splits the Andreev states at phase 0 and phase pi. We still have degeneracy. This is Kramer's degeneracy. It's not broken because we are not breaking time reversal symmetry due to spin orbit interaction. Then if we additionally add the scatterer in the middle, which is the same as in the Bagwell model, we have an impurity there in the middle. We are going to couple with the ballistic states moving in opposite directions, and this is going to open gaps at the crossings between with the ballistic states. So eventually, for a set of parameters like shown here, lambda 2 and lambda 1, these are two values of lambda, which is twice one with respect to the other, and some value of the transmission, we get two Andreev manifolds inside the gap, let's see, with a shape like this one. You know? This is, we have in this work, together with some Clay people, derived the transcendental equation, which extends the result from Bagwell for the case of having a spin orbit. So we have transmission lambda 1, lambda 2, and the position of the impurity in the channel, and we get such a spectrum for that case for these parameters. Okay, so now the question could be, well, what would we see in an absorption spectrum once we have such Andreev manifold, and we are going to shine microwaves and we're going to excite the system? What do we expect to see in the absorption spectrum, the microwave absorption spectrum? So the answer depends on what is the initial state. So for instance, if we are initially in the ground state, we only have, there are no ampere electrons, so we only have Cooper pairs. The lowest energy excitation for absorbing microwaves would correspond to excite the two quasi-particles in the Cooper pair into the lower Andreev manifold. This is for a fixed phase, like the dashed line here. So we would have these two quasi-particles excited into this lower Andreev manifold. And if we sweep the phase, we will see a line in the absorption spectra which is this red line here that we call the pair transition. However, if there could be other type of excitations, because we can have some excess quasi-particles. And if we start for a situation where there is an excess quasi-particle, a quasi-particle which is initially trapped in the lower Andreev manifold, there is an excitation which corresponds to excite this quasi-particle into the upper Andreev manifold. And if we forget about any possible selection rule, there could be up to 4 of these transitions, combining the 2 states in the lower manifold and the 2 states in the upper manifold. So if we sweep a phase for these transitions, we would get this dispersion, which has a very peculiar shape, because due to this transversal symmetry, we have this symmetry, we have this degeneracy at phase 0 and phase pi. But out of these points, we see that it's symmetric, and there are like 4 legs going to the left and to the right. And this is why we call these type of transitions, we call these spiders, because they have this typical spider shape. And these are what we call the single particle transitions. This gives an idea of what type of things we would expect in experiment. There are still more complex possibilities. This is, now like atomic physics, no? Because we have many types of lines. And so there are other possibilities for the even transitions, starting from the ground state. We can excite the 2 quasi-particles not to the lower Andreev manifold, but to the upper Andreev manifold. And this would give rise to this other pair transition, where you see the curvature with respect to the lower is the opposite. And we could also have transitions which are called mixed. We call mixed transitions, where the 1 quasi-particle goes to the lower Andreev manifold and 1 quasi-particle goes to the upper Andreev manifold. And this could give rise to these dash lines, red lines here. I talk about this later. And regarding the odd transitions, we may also have intramanifold transitions. We talk about this later, and this would give rise to these dash green lines here. Okay, so this is what we expect from this very simple model. And now we can ask, well, what do we see out of this in the experiments? Okay, so let me first mention, well, I told you that these transitions can be made using circuit-QED techniques, but let me briefly explain a bit more how this is done in the cyclic group. The start from a nanowire junction, like I mentioned before, this nanowire is placed in a loop. The loop, well, you have a gate which can control the density of electrons in the junction region, and the loop is then coupled to a microwave resonator, which is in a much bigger scale. No? So the characteristic of a microwave resonator is that there is some resonance frequency, which is for these experiments in particular, it was set at 3 giga or the order of 6 giga. And what is important is that this resonator has a large Q factor, and this is what allows to detect how the resonance of the resonator change with the population of the different Andreev states. So these measurements allows to detect a change in the frequency of the resonator of a few hertz on transitions which are of the order of gigahertz. So it's and there are two driving frequencies, two-tone spectroscopy. There is a microwave which is shined through the gate, which is a driving frequency, and there is another tone which is shined through the resonator to detect the shift in the resonator frequency. Okay, and this is how this spectra looks like. as a function of phase difference and a function of the driving frequency. And you can, there's many people here in the spectrum, but you still can identify this dispersion, these lines which disperse like pair transitions, and these spider-like shapes which disperse like what we expected for the single particle transitions. This is not particular of for a gate value, but you can see the same type of lines in another setting for the gate. We can also use this simple modeling, let's say, to fit the results with particular values of the parameters lambda and the transmission and the position of the impurity. We get, we can match this perfectly well with the theory for these single particle transitions. And out of this fit, well, we can get some insight on the type of the physical parameters of the system. Let's say if the nanowire has a certain diameter, has a certain length, we can convert these mesoscopic parameters into physical parameters. And in this way, we can deduce that the separation between subbands in the system should be of the order of 0.6 or 0.7 milli-electron volts. The chemical potential should be placed somewhere here in the middle of the subbands. We can even estimate the Rashba parameter, so the spin orbit parameter. All these numbers one gets from here are reasonable. However, we should warn that it's not a very precise determination of the parameters, because changing a bit the model, we can have a change in these values. But nevertheless, well, they are reasonable values, let's say. And well, if we also want to show that this is a spin effect or not, and not some other effect, we have to see what would be the effect of a magnetic field. And if we apply a magnetic field which is perpendicular to the nanowire, we distort the subbands, we break this the time reversal symmetry. This distorts the Andreev states respect to 0 and phase respect to pi. We can also apply a field in the direction parallel to the wire. This does not break the symmetry respect to 0 respect to pi, but the open gaps at these values between the Andreev states, well, same like the same as if we would want to define an helical state in the nanowire, no? And so this is, well, we compare this to the experiments. The fields that are applied are very, very small. The resolution in this experiment with finite field is not so good, but we see that roughly the opening of the gap for the parallel field and the distortion of the lines with respect to phase equal to 0 and pi also for the perpendicular field is demonstrated. One can also look at the prediction for the, any direction of the applied field, and we get also a nice agreement with the prediction from the theory. This was what we did already in 2019 in this paper with the Saclay people, and after that work, we started to ask about what about the other transitions, because these are the single particle and the pair transitions, the simplest. What about the other transitions? What about the pair transitions? The pair transitions, we said that would correspond to one of the quasi-particles excited to the lower Andreev state and the other to the upper. And so in this plot here, these pair transitions are these blue ones shown here. No? Now, in another experiment from the Saclay people with a higher stability, another design where they can have more stability in the measurement. This was the result that was obtained for the functional phase for different values of the gate voltage. Well, you can see lines which correspond to the spider, the red ones. Clearly, they are still there. Red lines which correspond to pair transitions like we had before. But there is a set of lines, these blue ones, which disperse very much like the pair transitions, but that in contrast to what we expect from this non-interactive model, at phase 0 and phase pi in the non-interactive model, we would expect the degeneracy of these lines. These are split. These blue lines are split there, phase 0 and phase pi. And they have this very peculiar shape, this that we call camelback shape. No? So what is the origin of this? Well, we started to wonder whether interactions could be playing a role. In principle, interactions in this system should be very screened, no? Because we have the nearby superconducting leads, there is the backgate. Interaction should be strongly screened, but still we can think there is some residual interaction. There could be some residual interaction, which we could model like a contact potential, Coulomb propulsion. No, we can also estimate the value taking values from the density of the electrons in the nanowires and the nearby gates that screen the interaction. We can estimate in a two-dimensional model, we estimate this parameter to be of the order of 3 electron volt per nanometer, which would correspond to a charging energy, if you consider the whole junction region, of the order of 30 micro EV, which is a value which is considerably smaller than the superconducting gap, so that we would not expect here to have quantum dot physics, let's say. You know, in quantum dots, if we have charging energy larger than the gap, we can have a transition to a pi junction. This is something which has been explored widely. But here, we are with a rather moderate interaction. So can moderate interactions can still have an effect? And the answer is yes, because now we're having we for these states where we have one quasi-particle in one Andreev state and one quasi-particle in the other Andreev state, we can have an exchange interaction. It's more like a 2-electron atom, let's say, and we can have then that the states can have an exchange due to this interaction, and this would split the spin in principle. This is the case without spin orbit, because we have the degeneracy, spin degeneracy inside. But already in this picture, we see that moderate interactions may lead to splitting of these states in which we have the 2 quasi-particles in the different Andreev levels by an order of 5 gigahertz, and we would split into a spin singlet, spin triplet. So we see that these mixed transitions can be split by interaction. So we would lose this degeneracy at phase 0 and phase pi, in contrast to the single particle excitations, which would be protected, still protected by Kramer theory, for a Kramer theorem. No? And this is what we have demonstrated going to a more elaborate model, extended tie binding model. We have to include many channels in the model because in order to see the splitting due to spin orbit, we need more than one channel. And we have to take into account the final lengths of the channel because we have more than 100 state in the gap. No? And this is what we did, not going into the technical details, but you see that by switching on the interactions for a particular value of the gate, we see how these mixed transitions evolve. They tend to be split into singlet and triplet, the prediction of the very simple model. But in addition, we have spin orbit. So that's why we don't have the degeneracy. Spin is not well defined due to the spin orbit. So we see a more complex pattern. A more complex pattern, which very much like which is very much like what we see in the experiment. We see this camelback shape here. We see the splitting of these lower lines here. So we are quite confident that what we are seeing in the experiment are these mixed transition, which are giving some insight to the interactions, which are very moderate. And this type of physics would not be possible to be detected by transport measurements. The tradition in mesoscopic physics is to study transport. In transport, you cannot resolve this effect because in this, if you look at the Josephson current, the total Josephson current, you wouldn't see any pi phase or transition. There is no transition here, but still you have this tiny effect due to the interaction. So it's extremely sensitive. These techniques are extremely sensitive to both spin orbit and interactions. Okay, and well, let me mention that this is a related work from the group of Michel de Boretti in Yale, which is also in archive. Okay, so let me see how I'm doing with the time. Okay, I can go to last discussion here, well, or two more things. We have understood from this theory what is the shape of the spectrum, what is the shape of the lines, but we have not a theory for the intensities. So for that, we need to study in more detail the coupling of the Josephson weak link to the resonator. We can make a model in which we say, well, the resonator is a harmonic oscillator with a frequency omega r, the frequency of the resonator, and we can couple, well, the Hamiltonian for the nanowire with a given phase due to the resonator. Through the fluctuations in the phase, this operator A dagger are producing the photons in the resonator, we can expand this to this the lambda parameter is controlling the amplitude of these phase fluctuations, which are induced in the loop. They are coupled to the microwave resonator, and so we can. This is what one would do typically in circuit-QED theory, you know. But what we have understood that for understanding these experiments, we need to go a higher order in this expansion, not keeping just to first order in the coupling to the phase fluctuations, but going to second order in the coupling to the phase fluctuations. And this would mean that we need to add this second order term. So with the second derivative of Hamiltonian respect to the phase. And if we then evaluate how the states are modified by this coupling, so the states correspond to a given Andreev state in the junction and a given number of photons in the resonator. So we couple them, and we can see how the energy levels of the coupled system are corrected to the first order. To the first order, we get some corrections due to the second order term in the expansion of the Hamiltonian. And to second order, we get a contribution due to the first order term in the Hamiltonian, which H prime is the first derivative with respect to the phase. So this is the current operator. Basically, this is coupling with phase and current. and this is coupling with the second derivative, which is like an inverse inductance in the junction. And then we out of this we can derive what is the shift in the resonator frequency due to a given Andreev state in the junction. And what we obtain is that there is a term, first term, which goes with the second derivative of the energy of the Andreev level with respect to the phase. And there is another term which has these energy denominators. These are the typical energy denominators which appears in the James Cummings type of description of a coupling in circuit-QED. However, when the resonator frequency is very detuned with respect to the Andreev transitions, this tends to zero. And what we only get is that the shift in the resonator is proportional to the curvature of the state with respect to the phase. So there are like two regimes, one which we call adiabatic, when the resonator is very detuned with respect to the transition, where the shift of the resonator goes with second derivative, and one which we call dispersive, where we have the shift in the resonator exhibit these energy denominators, which is the typical behavior one gets using the James Cummings model. So that's what is in this paper that we published in 2020, which is from adiabatic to dispersive in quantum circuits. And there is another thing that we need to understand the intensity of the lines, which is how we drive the excitations. And this is through a Hamiltonian, time-dependent Hamiltonian, which induces the transitions between the states. However, we can think of different ways to drive a system physically. One can drive a system through the gate, and in this case, one is going to apply a potential through the junction, which in general would be which would in general break this inversion symmetry with respect to the y direction, and this is enough in order to allow for spin flip transition. So when we break this symmetry, this pseudo spin I talked before is no longer conserved, so we can a couple different subbands and a couple different spins. And the other way to drive the system would be ideally through the flux, so modulating the flux. In this case, well, in principle, would couple through the current operator, and this would not induce spin flip transitions. In general, in experiments, this symmetry is broken always because there are gates, which are lateral gates. There are also these top semi-superconducting layers which break the symmetry. So in general, we can expect that these inversion symmetries will be broken. And well, this is something we comment in this work in collaboration with the group of Michel Deboré in Yale. And well, in general, well, using this theory, we can not only fit the lines, but also fit, let's say, the intensities qualitatively. And what we understand from this fit is the experiments are typically in the adiabatic regime, because the resonator frequency, 3 giga, is much lower than the transition one is considering here, which are higher than 10 giga, no? And this means that we are in the adiabatic regime, means that we are the shift, say the shift in the resonator, and so the intensity of the lines goes with the curvature. So that's we go from blue to red in this picture here, which goes very much in agreement with what is observed experimentally. And also, well, they say that we are driving through the gate and then and we are breaking this inversion symmetry, and that's why we see all lines. In principle, if there would be some selection rule, we would not see some of these lines, okay? Okay, so let me, if I have a couple of minutes, mention the other, yes, okay, thank you. Mention briefly the other possible realization of a qubit using these devices, which is the Andreev spin qubit, which is an idea which was already suggested by the group of Nazarov in 2003. And the point is to store the quantum information, not in the excitation, the energy excitation, but in the spin. Because we are breaking the spin degeneracy now due to spin orbit. So we can think of a quasi-particle which is trapped in the lower Andreev manifold. And this, well, we have the degree of freedom associated to the spin. So we could play, or we could store the information or use this degree of freedom as a basis for a qubit. The problem is that these direct transitions between the intra-manifold transitions, I also mentioned before, these are very difficult to excite. They are low frequency, and typically matrix elements between the states would be very small. So this transition is difficult to excite, but one can think of doing this transition indirectly through a Raman process, which means exciting the quasi-particle into the upper Andreev state and then going down to a lower Andreev state. This is something that we proposed in this paper that we published in collaboration with some of the people in the group of Michel Devoret, which is called stimulated Raman adiabatic passage. It's a type of Raman in which these two pulses are applied with some delay, and this optimizes the transition. But I'm not going to go much into that detail. Let me just mention that the group from Michel Devoret had performed already the Raman experiment in which they apply the two pulses simultaneously. It's a continuous Raman, it's not this stirrup process, but they apply these two frequencies, these two tones, in order to produce the spin transition, and they were able to observe the Rabi oscillations as a function of the amplitudes of these two transitions. Well, we did some theory in order to fit the data using Lindblad type equations. Not going to go in that detail. Let me also say that out of these experiments, they could also do time resolved measurements to observe the Rabi oscillations and estimate the values of the coherence times, which, well, for the moment are quite short, of the order of 50 nanoseconds. So, and there is, well, a lot of questions about what is the origin of the coherence in this type of Andreev qubit, and so on. Not going to go into that detail, but let's say that you can see that there is this other possibility for an Andreev qubit, which is based on the spin degree of freedom rather than on the energy degree of freedom. So for with this, I go to the conclusions. I want to stress this idea that the combination of hybrid nanowires with circuit-QED techniques is allowing to resolve these soul gap excitations with unprecedented energy resolution. I like to compare this situation to the situation we had with the atomic physics, the beginning of the 90s, where you could understand the atomic structure using visible spectroscopy or ultraviolet in spectroscopy. So this microwave spectroscopy is also allowing us to understand with this spectra with a resolution which cannot be obtained in transport experiments, for instance. In this way, we get this evidence of the fine, what we call the fine structure, because it's similar to the fine structure of an atom, no? Due to spin orbit interactions. And we also, well, we could also fit the lines with using a very simple multi-channel model. We have also the evidence of interactions, even if they are weak, we can detect this effect of these weak interactions in the mixed pair transitions. Well, we have developed this theory of circuit-QED detection and understanding, well, qualitative understanding of the line intensities. And well, finally, we have this coherent manipulation of trapped quasi-particles in well, due to the spin transition. No? So we see, demonstrate in a way that this Andreev spin qubit is possible, although the coherence times are very, very short. And well, there are many open issues, understanding what is the excess of quasi-particles. This is not only exclusive of this problem here, but also from this conventional qubit, the excess quasi-particles is a big mess, it's a big problem. What are the mechanisms for the coherence in the Andreev spin qubit? Going into the topological regime is a dream which many people have. Detect the Majoranas not from transport by this type of experiment would be extremely interesting, although experiments in this direction still have not been produced. And with this, I would like to acknowledge the people who participate in this work. I would like to acknowledge Sungwoon Park, who is a postdoc working with us at the Autonoma since many years now. I would also like to thank the people in Quantronics, Cyril Metzger, Leandro Tosi, and Marcelo Goffman, Hu Potier, Christian Urbina. Leandro Tosi is now in Bariloche. I also like to thank Andres Reynoso in Bariloche, who participated in some of the work we did with ACLE. I also like to thank Francisco Matute, who is now a PhD student at the Autonoma and who did most of the work on the interactions and the mixed transitions. And well, also thank the people from Copenhagen, which are producing the nanowires, which are used in ACLE. Also thank the people in Yale, Michel Devoré, Bala Fatemi, and Max Hayes. Javier Cerrillo was a postdoc here who participated in this spin qubit work, and also thank Attila Jerezdi, who is participated also in the collaboration with Yale. And with this, I thank you, and I'm open to receive questions.
Awesome, thank you very much. So yeah, I guess I can start with the first question and I'll let the audience do it. So the qubit was very nice, a demonstration of, or at least, yeah, that experiment showed a very nice demonstration of the possibility of using these quasi-particle states as qubits. So one question I had was, if you thought about what would be the mechanism to actually couple multiple qubits together?
Yeah, in principle, as these are flux qubit, no? In principle, these qubits, if you want, as I mentioned here, they're flux qubits. So we could couple them inductively, no? And well, there are different ideas how to couple the qubits. In principle, the most simple idea is couple them inductively, place another loop nearby, or you can couple them through microwave bus, no, like like you do in transmon qubits, actual transmon qubits. But although this requires much more space in the chip, no, this is what people is trying to reduce. No, the idea of these qubits would be that one could integrate the qubits in a much more reduced space. No, and we can also think of qubits. Well, defining qubits in the same wire. Like say you put a junction and another junction in the same loop, and then you could also think of, yeah, do you have two junctions, with some gate in the middle to control the coupling? This could also be an idea. We have in this NQC project mentioned that. So theoretically, we can do many things about these ideas to couple qubits. Think of an Andreev molecule, so one junction coupled to another junction, and control the coupling. But experimentally, they are still far. I would say, because the problem of stability and the problem of the coherence still strong. But well, we are working on this. We have some hope that this could be interesting. If not technologically, there is very interesting basic research to do there.
Yeah, exactly. All right. So yeah, Noah, go ahead and unmute yourself.
So it's a theoretical question, of course. What, in theory, do you think would be the scale for the 2-qubit coupling?
Sorry, it's a little hard to hear you.
Yeah, difficult. I understood something about the coherence, but I don't know if you're talking about the Andreev level qubit or the.
No, the question is a follow up to the previous question. So it's just what would you expect if we took one of those two scenarios you just described for the 2-qubit coupling frequencies? You know, just the order of magnitude, gigahertz, megahertz, kilohertz. For trapped ions, it could be kilohertz. For flux qubits, tend to have gigahertz.
No, well, I think you can tune the coupling, at least theoretically. No, suppose you.
Yeah, of course.
Oh, sorry. I should share again. Maybe. I mean, you can say, well, I put some region in the middle, and what is depending on the length of this region, I mean, the coupling is going to scale like the length over coherent length. So, oh, well, I'm doing very badly. But let's say the coupling could be, it can range from a few megahertz to whatever you wish, no, in principle. Depends on the dimensions you put here. So there would be like an anti-crossing of the qubits, of the Andreev states, and yeah, this could be much less than a gigahertz. So then I think in actual qubits, well, what are the typical coupling? The order of magnitude of coupling between qubits is also much less than a gigahertz, probably in a megahertz.
For trapped ions, yeah, it could be like that. With the expression you drew, it comes to mind that the thing in front would be the gap. So that seems like it sets a hard cutoff, like what you're thinking about is either minus L over C times some energy scale. The energy scale should be the stiffness.
Yes. You could say yes.
Like that.
Yes.
Put
it's a very rough estimate. Very rough estimate. Not really something to take seriously. And well, one can say, well, if in the middle we have a nanowire and we have gates which can control the density here in this in the region, would be much more complex than that. No? We have done some modeling of this, although not published, really, not published work. And but I think this would not be the more difficult. No? The more difficult experimental problem would be to really define this geometry and be able to couple it with strongly enough to the resonator. And
what about for your flux idea, the one you mentioned, where you have two guys coupled, I guess inductively you might say, through the loop. So you put two links in a loop. What do you think would set the scale there? Here it seems to be the gap modulo this gate business.
Yeah, well, here you have like a mutual inductance, no?
Yeah.
And so this depends on the length of this ring here on this part of the ring. So what's a mutual inductance here? I will not be able to give you a number, but for instance, when you couple this to the resonator, they try to maximize the mutual inductance in order to have a stronger coupling to the resonator. So then they insert directly the junction into the resonator structure, no? And then this way they have like a galvanic coupling. So maybe even put this one over the other, no? One on top of the other, and you see in the type of the values that when they get for the phase fluctuation, the 0 point fluctuations is a measure. The 0 point fluctuations which are induced from the resonator to the junction is a measure of the coupling, and this can be of the order of 10 to the minus 3 or something like that, 10 to the minus 3. So 10 to the minus 3 means that you modulate, that you can modulate the phase by that amount. You have to convert this into an energy.
I wonder what you think might be the limits to the number of qubits you could integrate with this kind of scheme. That the motivation seems to be about integration, right? 5?
Yeah.
1?
Yeah.
What was that limit?
What's the limit? This is a difficult technological question, no?
But maybe there's some physics.
Of course, I'm not an expert in that, but
neither am I. But
the
I'm thinking of the energy gap you might get. If you, like, say we couple 5, right? It somehow brings to mind single junction. So we think about these guys. There's a qubit on the first, this qubit in the second, the qubit in the third, and they're kind of a quantumizing model. You know, kind of like a wire, supply of wire. The mini gap you get between the 000 plus 111 and the 000 minus 111, you might think it'll go like you drew, either minus L over C, where now C is set by the single qubit, we call transverse field, single qubit phase flip, and J is the coupling, the frequency of the coupling between the two guys. From this point of view, you'll hit the Hawking radiation limit from the Earth's gravity at 5 or 6 qubits. And I mean,
I think you are more expert on this.
It's a physics argument, not technological. It's just
the
expression you wrote. It's e to the minus L over C, right?
No, but this is I understand, and I understand
length within this 5 qubit.
Yeah, in principle, what you need is to couple to the nearby qubits. No, you are not coupling to distant. No,
right. Just local coupling. So that'll be the J instead of the phase stiffness first within this single. So before we were calculating the coupling between 2 qubits. Let's just call that J. So it's delta e to the minus L over C, where C is the real coherence length of the superconductor. Okay, so that's J. Then for the transverse field, thinking of an icing kind of picture, the transverse field is just the phase slips within a single qubit, right? And now you do the quantum icing with 5, length 5. It's a Majorana wire, 3 fermions. You get an energy gap, exactly the same expression, but now it's J e to the minus L over C, where C is the correlation length for quantum transverse icing model, and the J is the thing we just tried to calculate a second ago. We're kind of waving our hands, maybe it's up to 1 gigahertz. So when you plug in the numbers, I think what you find is around 5 or 6 qubits. That splitting J e to the minus L over C is something like the Hawking temperature of the Earth's gravity.
I see.
You can screen the CMB. You can put your thing in a cryostat, but if you want to be at rest on the Earth, you're going to bake your qubits from the heat from the horizon of Earth's gravity. The virtual particles coming in and out of the vacuum. It's not a technological point. It's purely physical.
I see. Well, you have the answer then. So,
so do we give up doing science?
I think, but your answer in a way is not dependent on the type of qubit. No, you say, well,
there's a logarithmic dependence.
Yeah. Okay. So this is an interesting issue, something that could help when we reach this issue of coupling many qubits. For the moment, you see we are in a much modest stage, no? But I think, well, if this is a problem for conventional qubits, as it would be the same here, no? I don't think we are going to change that problem, no? The only thing I say is that this would allow this type of qubit would allow a larger integration, no? It's only that. Then the scale of a coupling you need for the say to work as a quantum computer, of course, this is another issue which can be solved separately. No, I don't think the scalability or the problem and this problem you're mentioning are related. No.
Maybe just the relation is error correction. So when you want to do error correction, you make a cat state, right? But try and make a cat state with more than 5. What you find is, okay, so for trapped ions, it would be 8. There's a logarithmic scaling. So trapped ions are a little bit cleaner, the longer lived and all that. You get 8. So try and make a cat state with 9. And what you find is it's a useless cat state. You're trying to use the phase coherence as your reference to correct your qubits. And what you find is your ancilla is just no good. It's basically a thermal state.
I see.
So this is the conventional multi-particle interference, kind of picture for how you're going to do. You don't make a measurement. You just interfere your qubit with this ancilla that's in the cat state. The issue is you can't scale the cat.
I see. Right? I see.
That's the connection.
I see. Thank you. I would like to think of it in more detail. Yes, if you can send me any reference, I would be grateful.
We have a proposal out there. We can say
okay.
Unfunded proposal.
Very good. So you can tell me more about how to couple it, make many qubits out of it.
Maybe the first quantum gravity detector. We use your
yes.
qubit to detect the talking radiation thing from the Earth's gravity.
No, that could be interesting. Yeah, could be very nice. Please send me a message with these references.
That sounds very interesting. Do we have any other questions? I think most of the audience is. Yeah, okay. So I guess this is, yeah, if there's no other questions, I can thank the speaker. Thank you, Alfredo, for your very interesting talk. And yeah, look forward to seeing everybody next week.
Okay. Thank you, Phil. And good night, everyone.
Good night.
Well,
Bye.
good night for me.
Yeah, exactly. Good afternoon for us.
Yes.